Show. I guess like a few remarks before I start. One, I tend to talk really fast, so if I do that, please like slow me down. It's like something I'm really trying to work on. The second thing is like I have a few friends here who are going to be helping me as I talk. So they're all Pokemon. If you don't know Pokemon, I've kind of given you like the rundown here so you can like keep track of who's who. So the first is going to be Alice. The second is Bob, and the third is Evie or Eve, I guess. And like, if you can't keep these straight, Alice will always be to the left of Bob, and then Eve will be doing something weird. So hopefully that'll be good enough. Okay. So the problem I'm going to be talking about today is going to be about an area called interactive coding. And interactive coding is like an interactive variant of error correcting codes. So let me just start by, I guess, talking about error correcting codes so we're on the same page. Okay, so here's the problem. Suppose that like Alice here has like an input X, which she wants to communicate to Bob. Of course, she could just send it to Bob, but what happens if the channel is noisy? So in particular, we're going to say that there's an adversary Eve who is going to corrupt some of the bits. So for instance, like if Alice had meant to send 0, 1, Bob might receive 1, 1 because Eve corrupted a single bit. And like even if Bob knows that Eve corrupted a bit, it's not clear if Alice intended to send 0, 1 or 1, 0. So the question is like, is there a way that we can like, send an encoding of a message X instead so that Bob can still learn X even if some of the bits are corrupted? And throughout this talk, this is what's called an error correcting code. So we're denoted by ECC. And so in general, ECC of X would denote the encoding of this message X. So there's two types of corruptions we're going to be looking at in today's talk. The first is errors, which is when you can take a bit and flip it. So you change it to a different symbol. And the second is erasures. So you take a symbol and you erase it, leaving behind like a placeholder where the symbol was. So you know the position of the symbol being erased, but not what originally was. So there's like three main like properties of error correcting code that people have studied throughout the years. The first is distance or resilience, which is sort of at like trying to gauge like how many bits you can like protect, like how many bits of error can you protect against. The second one is rate. So how efficient is the encoding? How many extra bits are necessary to create the encoding of X? And the third one is computational efficiency. So ideally the codes that you use should be like encodable and decodable and like, polynomial or hopefully even linear time. And in this talk, my focus is going to be on resilience. Okay, so let me maybe be a bit more formal about the definition. So for us, an error correcting code is going to be a family of maps, mapping from an input domain 0, 1 to the K to messages of length n over some like alphabet sigma. And it will have relative distance delta if for all two input messages that are distinct, the number of bits that are different between the encodings of X and Y is at least a delta fraction of the total like message length, the code word length. And a relative distance of delta implies resilience to delta over 2 fraction of errors, or to delta like as in delta erasures. Okay, yeah.
Like as stated, this is a trivial theorem, right?
Yes, it's just a property, yes. Or like, yeah, it's pretty simple. Yeah. So I guess the question you could ask is like, what is the best relative distance you can get for an error correcting code? And it's known that if you have a large alphabet, then you can get relative distance 1. But over the binary alphabet, the best you can do is 1/2. Okay. So let me give you an example. So suppose Alice is trying to send over like a 2-bit message, so 1 of 4 possible messages. And so she's going to do this by encoding one of the 4 messages into the right-hand side, like one of the 4 code words. And if you look at these 4 code words carefully, you might observe that between any 2 code words, like the number of bits that are different between the 2 is 2/3 of the total bits. And this implies like resilience to 1/3 errors or like 2/3 erasures. Okay, so at this point, you should be asking the question, like in the previous slide, I told you that you can only win 1/2 like distance for binary codes. This is clearly a binary code with distance 2/3, right? And I guess the key point here is that in the previous slide, we were concerned with like a family of codes. So like you want to look at the input size getting like very large, in which case then the maximal distance like decays to 1/2. But if you only have like input size 2, then you can actually get a better like distance. And this is going to be like the key point that we're going to be leveraging in later today's talk.
Probably in the previous slide, you also want the code to still be exponential in size.
You actually don't need that. Oh, I guess like if you want exactly 1/2, you need exponential size.
So both of these really only make sense if you want a large code. 'Cause you can certainly pick like all zeros and all ones, and you will get a ridiculously large distance, but it's a ridiculously useless code, right?
Yes. And I also want to point out that when I say like about 1 or about 1/2, I mean like 1/2 minus epsilon or 1 minus epsilon. And like your alphabet size could be like 1/epsilon, for instance. And like the length of the encoding will be like k over like epsilon squared or something. So it'll be linear in like the input size as long as you fix sort of like the separation from 1/2.
Do you have any assumptions on the rate as well?
In this, well, the best you can, I mean, so you can do like positive rate if you like view epsilon as just like fixed. And that's what we're really going to use in today's talk. I mean, that's like kind of the, I think there's like, it's known that if you want relative distance 1/2 minus epsilon, you can only do rate like 1 minus 1/epsilon, wait, no, 1/epsilon squared or something. Or sorry, maybe epsilon squared is the right way.
It's for the binary is epsilon squared log 1/epsilon. The upper bound is lower than that. But
okay. So I guess the question now is like, what about interactive communication? So far, we've had Alice try to send over a message to Bob, but like in many systems, there's interaction that goes on. And so like the question is like, how do you protect against errors that are happening to like an interactive protocol? So let me just give you an example. So one example of an interactive protocol is like the game of chess, right? So Alice and Bob are going to take turns making moves. And they're going to send their moves to each other. And by the end of the game, they'll have like a game state in mind, and they'll decide on like who wins and who loses. So suppose we're trying to like make an error resilient version of chess. So maybe like the first idea you have is let's just encode every message with an error correcting code, right? Because like then it's like somehow it feels more resilient. So this seems like a great idea, and it gets us like this new chess game, which is going to have them each sending like an encoding of their move every turn. But what if the adversary comes in and corrupts maybe just the first message so that it looks like Alice made a different move? Then now Alice thinks that she's made the move E4, but Bob thinks that she's made the move F3. And if they continue the simulation, by the end of the game, they have like different game states, right? So like they'll be playing different games the entire time, and perhaps they won't even know who won and who lost. Like they both think maybe they both won, or maybe they both think they both lost.
You're assuming that the errors can be adversarially distributed over them.
Yeah. If you want just like random errors, this is like a pretty good solution, it turns out. But like we'll be looking at when there's like actual adversary who is like adversarially choosing the corruptions.
So I guess the point is that this is still a very tiny fraction of the whole game, but you can completely corrupt it.
Exactly.
Yeah, the length is the whole thing.
Yeah, that's actually what I was going to say next. Like, so like the problem here is that, this only like requires a very small fraction of corruption. It's not even a constant fraction, right? Because there's so many rounds. So if you want like a constant fraction of error resilience, then this is not going to work. So the kind of the difficulty is constructing like a compiled protocol such that like you can kind of detect when these errors happen and go back and fix them and so on. Okay, so this is a problem known as interactive coding. It's due to Showman in '92. So you're gonna start with a noiseless protocol, pi0, which is gonna be like a protocol run on Alice and Bob's private inputs X and Y. And the goal is to compile it into like a noise resilient protocol that can like, I guess like handle noise that happens. And the correctness guarantee, I guess, is by the end of the protocol, they should both be able to learn what the original like noiseless protocol was supposed to be.
So the adversary can decide on where to corrupt based on previous messages during the protocol?
Yeah.
So it's online
This
kind of.
online corruption is not a, like, you don't have to decide beforehand what you're corrupting. So just like for error correcting codes, there's sort of like three main like properties you might care about for interactive coding. So once again, like resilience, rate, and computational efficiency. And there's been like many works on just this area, like, you know, for all three properties, but also for like other models like insertion or deletion channels, feedback channels. There's adaptive models, like the model we'll be talking about will be called the non-adaptive model. There's like multi-party models, relation to like circuits, quantum, etc. So there's just like been a lot of work in this sort of general area. And once again, like my focus in today's talk is going to be on this resilience property.
People ever look at the number on forehead model?
Sorry?
People ever look at the number on forehead model?
The number on what?
Number on forehead, where each player knows all the other messages, but not itself.
Oh, that's an interesting question. I have no idea. Yeah. Yeah, that would make sense in a multi-party setting, right?
Yeah, but it's not the standard. I guess the standard
Yeah.
would be like 3 players or each.
Yeah, it's
Yeah.
dual.
This is all for 2 players, right?
Yes. Yeah, but there is also work in like multi-party or like, yeah. But it gets a bit messier, or at least to me, it feels like a little bit messier just because you have to look at like what the graph looks like and whatever. So I think the 2-player model feels very like simple to me, just like what I like about it. Okay, so maybe I should be a bit more precise now with the actual model. So once again, we have a noiseless protocol, and the goal is to compile it into like a noise resilience protocol. And we're the noiseless protocol, or sorry, the noise resilient protocol. We're going to make the assumption that like every round, a fixed party sends a single symbol to the other party. So like if you want a single party to be sending many bits consecutively, you just have many rounds of them sending bits. Yeah, so like I guess, so the order of messages is like up to like the designer of the protocol. But it's just important that like every round, both parties know who is supposed to be speaking and who is supposed to be like listening. And then we're going to measure error or erasure resilience in like a fraction of rounds. So we'll say that the protocol is delta error or erasure resilient if for any corruption of delta n of the rounds, Alice and Bob can still determine what the original noiseless protocol is supposed to be. So the main question is, what is the optimal error or erasure resilience possible for an interactive coding scheme over the binary alphabet? Okay, so I guess like, so what is known? So here I have a chart. I've separated it into 2 categories. So the first is like large alphabet and the second is binary alphabet. And I filled in so far the results for error correcting codes. So just like recall that error correcting codes over the large alphabet can have distance like basically 1. And for binary alphabet, they can only have distance like 1/2. So you get 1/2 and 1 or like error and erasure resilience over the large alphabet and 1/4 and 1/2 over the binary. Okay, so for interactive coding, what do we have? Well, so the first result was by Shulman in '96, who showed that who constructed a protocol that was over the large alphabet and is resilient to 1/240 fraction of errors. Yeah, and then I think the next time this problem like of actual optimal error resilience was like initiated, like as an active field of study, was in the work of Braverman and Rao in 2011. And they showed that for the large alphabet, the best you can do is 1/4. So they constructed a protocol and showed like an impossibility result.
When you say large,
Like 1/epsilon squared size alphabet, and you want like error resilience like 1/4 minus epsilon. Yeah, I kind of dropped all the epsilons just because they're annoying, but yeah. And I guess for intuition for why you should expect 1/4 to be like the right number. Well, in an interactive like protocol, you have 2 parties with like their own like hidden input. And by the end of the protocol, they want to compute some function of the 2 parties' inputs. So they're like sort of sending each other information in a sense. And so there's like sort of a 2-way like, like communication happening, and each direction is resilient to like, 1/2 errors as, per the ECC. And like, of course, like the construction is much more complicated than this because like you have to simulate like an interactive protocol. But this is sort of the intuition for why 1/4 is like the right number at least.
I'm not trying to understand. So if each side has half, why is it 1/4?
So if you like imagine like, oh yeah, so I guess like each direction is resilient to 1/2. And then you have two directions. So you take whoever speaks less and you like corrupt half of their communication.
Okay, I see. Oh, so if it's very unbalanced, no,
Then you just pick the smaller person, yeah.
but that could.
I think the difference is if you like of half the input you corrupt just one, that already destroys the community, right? If between
Okay,
you
so it's
and
enough to
me,
corrupt half from one of the sides.
that's right. Like if you didn't understand what I meant, then everything is moot.
Yeah, great. So, and like this like 1/4 construction over the large alphabet translates to a construction over the binary alphabet of 1/8. And the reason for that is you can take a large alphabet symbol and replace it by like a binary code of relative distance 1/2. Sort of like concatenated codes, if you know what those are. And that will give you 1/8.
Just a random question. So these kinds of results, I mean, you should account for something like keeping the communication complexity or.
Yeah, well, I think all these are positive rate results. Positive rate means like the amount of communication overhead necessary is like only a constant, like multiplicative factor.
Okay.
Yeah, otherwise you could just do
Yeah, exactly.
PCC,
Otherwise,
and then it's
the
very
whole
trivial,
thing
yeah.
using an error correction code, right? So, okay.
Yeah.
Okay.
Okay, yeah, and I guess like the 1/8, it was not known to be tight, like this is just a construction. Okay, so for erasures, so the work of Franklin et al. Studied the case for erasures. And it was known that they show that you could get 1/2 for large alphabet. And the same like impossibility result holds for like binary alphabet also, just because like the binary alphabet is smaller alphabet. And I guess like the intuition for that being the upper, like the impossibility result is you can just erase the party who speaks less, right? Like thereby silencing them. So yeah, they can't communicate anything at all. Then there was a work of Affiliation, Gillis, and Hopler, who studied, I guess they have like, for us, they'll have like two main results. So the first is they were able to construct a protocol with 1/3 erasure resilience over the binary alphabet. And the second one is they showed an like impossibility result of 1/6 over for errors over the binary alphabet. And their upper bound of 1/6 actually holds in a stronger model called the feedback model. I'll talk about this like in a few slides, but the important thing here is that it's a stronger model where Alice and Bob have strictly more power. So if you just remove this extra power that they have, you get this like impossibility result of 1/6 also.
So the strategy of, let's say, erasing the party that speaks less, I mean, it wouldn't work if the length of the messages can be adaptive or changed. So
Exactly.
you want to allow that?
Yeah, so we'll be the non-adaptive model. So let me see. Oops. Yeah, so every round, like this can be a fixed party beforehand who's sending a symbol.
A single symbol. Oh, okay.
Yeah, so the order of speaking, who's speaking every round is predetermined. It's true that if you look at adaptive protocols, you get a lot more power just because you can like choose who's speaking, and this can also convey information. Let's see. Okay, and so for a while, this was actually just what was known. It was known, like, you know, if the answer should be 1/8 or 1/6, if it should be something in between. I think it's kind of like a fascinating thing that this was open, because like for error correcting codes, like the answer is like very like easy to get. It's like you can probably do it for a piece of assignment, for instance. But like, yeah, but for some reason, like this, like the answer for interactive coding was so elusive. And then the breakthrough of Affiliation, Cohen, and Saxena in 2020. And they improved the construction for errors to 539. And I don't know if it's immediately clear, but like it is actually bigger than 1/8. Yeah, and so this is like a really cool result. But still, it wasn't really clear if it was supposed to be like 539. I mean, probably not, because that's a really weird number. But like, you know, if it should be something like closer to like the 539s area, or if it should be closer to 1/6. And same for erasures, like it just wasn't really known like what the answer should be. So that leads me to like our work. So we constructed protocols, I guess, for both scenarios, matching the best known impossibility results. So I guess we figured out what the optimal error and erasure resilience are supposed to be.
Is there any intuition for the lower bound?
The lower bound, like sorry, these two?
Yeah, the ones.
Oh, this one, yeah, let's see. Yeah, like you can construct I don't know, I guess like I don't know how to explain it besides just giving you the proof. It's a weird thing where you like take 3 different like possible Alice messages and you do an attack where you consider like the majority bit that is being sent in every round, and you pick that, you corrupt to that one. And at the end, you show that like there's 2 of them that must be like was supposed to be 1/3 away. Makes sense. But yeah, I don't think it's like that clear. Like it's not that easy of a, I guess, a result. Yeah. Okay. And I guess like other thing is like all of our protocols are positive rate and computationally efficient. We actually have 2 works. So the first work, like our 1.6 protocol, was like exponentially inefficient, but we improved it this summer. So I guess in a sense, like we seem to have like the best results in all 3 directions you might care about. So error resilience, rate, and efficiency. Yeah, so I guess like for most of the remainder of the talk, I'm going to be talking about just a 1.6 result. I think that's a more interesting one of the 2. But let me just like spend a minute and tell you a bit more about the erasure result, or just like give you like maybe a bit more, like talk a little bit more about it first. So I think like the interesting thing about the erasure result is that in general, if you go from a binary, like a large alphabet to a binary alphabet, you get like a distance reduction, right? Like in like large alphabet ECCs, you have distance 1, but like for binary, only distance 1/2. So in general, it seems like the resilience to like decrease when you go to a smaller alphabet. But like interestingly enough, like if you go from like if you have erasures and interaction, you actually preserve like the erasure resilience, which I think is pretty interesting. And maybe like the best intuition for why that is like when you have erasures, you can never receive wrong information. You can only like not get information, right? And if you add an interaction, you can then like wait until you get the information that you need. So I guess the challenge then is just to construct a protocol in which you can sort of wait like correctly with just the binary alphabet, but we do that.
So what do you mean by wait until, like it's not adaptive, right?
It's not, yes, but like you can imagine like I'll send you like the first bit, and then you can be like, hey, I didn't get that. Can you send it again? And then I'll just keep sending it until you receive it.
Oh, so the protocol. Oh, okay.
So it's not adaptive because the structure will be me send you a message, you send me something, and so on. But like what you send every time can like just be like, oh, I haven't received it yet. Please keep sending it.
So one party tries to send and the other one just says whether they got it or not.
Yeah.
And in the end, they have the other input.
Yeah, that's like one way to think about it. Yeah.
Fair enough.
Okay. Yeah. So I guess maybe some more intuition for the 1.6 result. So I told you earlier, there's this like other model called the feedback model. And so I think now's a good time to talk a bit more about it. So in the feedback model, you have like a channel which gives you this noiseless feedback at every point. So every time you send a bit, you instantly learn what was received at the other end. And this is for free. So like you learn like, you know, whether or not the bit was corrupted, whether or not they received it correctly. And you just get that information for free. It comes at no cost. It's just like, you know, it's just always there. And this allows you to basically like always tailor your message to like what the other party like needs to hear, right? Because you can always choose like the best piece of information at every point. Yeah. So it was shown in the work of Efferman, Gallis, and Hopler that the optimal error resilience in the feedback model is 1/6. Yeah, and so our result, I guess, that we can actually get 1/6 without this like feedback channel. Means that like this like noiseless like free feedback doesn't actually grant any additional power in terms of error resilience. And I do want to say though that like even though we don't require this like noiseless like free feedback channel, we will use some of the ideas from feedback in our protocol. So like instead of having like the free feedback just like sent magically, we'll incorporate it into like sort of the communication that's going on. Okay. Any questions at this point? Okay, so I guess for the rest of the talk, I'm going to be talking about, I guess, just like some of the ideas that go into this like construction that we have. And I guess I was gonna try to make a joke. I guess I'll try to make it and see if it goes well. So I was trying to find pictures of like Eevee, which is like Eve, wearing like costumes of like Bulbasaur or like the other Pokemon. Because like she's pretending to be the other ones, but I couldn't find that. So she's wearing like, so I don't know very many Pokemon, but she's wearing some other Pokemon costumes, but pretending to be other Pokemon. Okay, cool. So I guess like we're gonna make one simplification for this talk. That the protocol is going to be for message exchange. So we're gonna suppose that Alice and Bob both have like an input message and they want to tell to the other person. Of course, this doesn't really capture like the full like interaction, that like interactive protocols thing, but this will contain a lot of the key ideas at least. So hopefully this will like help you understand a bit of what like our ideas are doing. Okay, so I guess like, what's the easiest thing to do? Well, the easiest thing is to just send over like encoding of X and Y. And let's look at what the error Lillian says here. So if you have Eve who is going to corrupt some of the communication, well, each of these messages, each of these code words has relative distance 1/2. And you have two directions. Each direction is resilient to 1/4 errors. So you get 1/8 errors against it. Okay, so I guess like what's the issue here? I mean, clearly this is not 1/6, right? So like, why is this not 1/6? And the reason it's not 1/6 is because like both of these codes have relative distance 1/2, right? Like Alice is sending over like X, which is like less K, which is very large. And the best you can do to encode K is to use a relative distance 1/2 ECC, right? So but like before, remember I told you, if you're only sending over a 2-bit message, you can get relative distance 2/3. So that's our first idea. So if the messages they were sending were only 4 options or like 2 bits long each time, you could actually get the 2/3 like distance that you need to get like 1/6 instead of 1/8. Of course, like if you just send over 2 bits, I mean, you have K bits as input, you can't convey everything, but that's where interaction comes in. So the hope is like using many rounds of interaction, sending maybe like, a couple bits of information at every point, you're able to convey like the entire K bits of information over like many rounds.
2/3 is the highest you can get for any size.
No, so if you had only 2 options, you could get distance 1 just from the all 0 or the all 1 string.
Okay. 2/3 is the next.
Yes, 2/3 is the next one. Yeah, so 3 messages, 3 options is also 2/3. Yeah.
Oh, so one thing, you didn't talk about randomized protocol versus deterministic.
Oh, yes. Yeah, so our protocol will actually end up being randomized, which is a little interesting. Like, I guess in general, in interactive coding, like all the protocols are deterministic up until you want computational efficiency, in which case then they introduce randomness. But for us, we actually just like, our protocol is inherently randomized even before introducing computational efficiency, which is like sort of interesting. I'll have that as an open problem at the end also. So if you guys want to maybe deterministic.
So there was no known difference between the two.
For like, for upper bounds, like the impossibility results and stuff. Yeah, so it will hold also, like the same impossibility result.
So I know some of the other works were using tree codes.
Mm-hmm.
Is this not kind of deviating from that, or is this?
Yeah, so tree codes are a good way to make a protocol like positive rate, because instead of sending over like the entire ECC at every point, you can send over like only the next bit of the ECC, which will like, become a long chain. So we end up using a tree code-like structure in making our protocol positive rate. But I guess for now, what I'm showing you will be sort of like a terrible rate protocol. Okay, so this idea is okay. Okay, so I guess maybe let me show you like how this idea like will work, I guess, in practice. So I guess for now, let's assume that only Bob is going to try to learn what Alice has. So Alice is not trying to learn anything about Bob. We're also going to assume that Bob is not corrupted at all for now. So we're only looking at like Alice side errors on this. So this is what I call the question answer approach. Is also probably like, feedback or whatever. Yeah, and so suppose that, okay, so basically what's going to happen is Bob is going to have a guess for X. We're going to denote it by X star, and it's going to start as an empty string, and Alice at every point is going to tell him like the next bit of X, and he's going to build up X over time, like making it longer and longer with every round. Okay, so at every round, Bob is going to send over X star to Alice, and basically asking the question like, hey, here's my guess for X, like how should I update it? And Alice is going to respond by either telling him the next bit or that maybe the last bit was wrong and you should like, delete the last bit so then you can like rebuild it from scratch. So that's 0, 1, or that's supposed to be a back arrow, but I guess it's just a box. So a box would mean like the eraser, I guess, for this case.
Wait, so sorry, what are the 3 choices?
So either 0, 1, which is like the next bit of x.
Just the last bit that's wrong.
Or like, well,
Or
yeah.
back one.
Yeah, like, so
could repeat several backs. There's a lot of things wrong, but I imagine that you wouldn't even let the procedure go on if there's too many.
Yeah, so I guess like, yeah, so if there's an error early on, Alice would like try to send like erase for many rounds. And if like Bob keeps like impending it, it means like lots of errors have happened. And so then I guess, yeah, then like at some point the adversary will run out of budget and we'll have to like start sending like allowing the correct backspaces to go through.
So the adversary can't affect the length of the messages.
No. Yeah, so we're looking at just errors or erasures, not deletion channels, which are very complicated. So, yeah, and this will continue for all the rounds. Does this make sense? I guess as a framework. Okay, and yeah, so this is supposed to be a binary protocol, but at this point, Alice is sending like 3 things. So let's address that first. So we'll have Alice send one of 3 messages, 0, 1, 1, 1, 0, 1, or 1, 0, 1, or 1, 1, 0. And these have relative distance 2/3. Okay. So I guess like the key point is that every time Bob receives a bad update, one good update will undo it, right? So like if he receives like a bad bit, then like one backspace will like undo that. Or if he receives a backspace unintentionally, like one like reappending the correct bit will like undo it. So as long as there are more good updates and bad updates, Bob will like learn what X is supposed to be. So okay, assuming Bob is not corrupted, then this protocol is resilient to 1/3 errors in Alice's communication, because it's like every other message can be corrupted and the distance 2/3. Okay, it seems less okay. Okay, let me try it again. Okay.
I was wondering if there's any problem with the termination of the protocol.
Oh, yes. Yeah, so usually you take the protocol to have like k over epsilon rounds, and then and then you just like keep doing this until the end of the protocol. And the idea is just like as long as over the entire like k over epsilon rounds, there are more good updates and bad updates by like a factor of like k, then you've learned X.
Right. I think that's not what I asked. So the idea is that, okay, so I know that the final string that they're trying to compute is length 15.
Oh, okay.
But what if I'm quite unlucky and nothing happens until bit 14, and then on bit 15 I get something wrong, and then Bob thinks, oh, I'm done. I already have a 15 thing on my hands, but actually the last bit was wrong, so they actually should continue.
Yes. So I guess like what will happen is like Bob will continue like he'll be continually updating his guess until the end of the protocol. So he'll never terminate early.
You don't terminate.
Yeah.
You just keep going.
You just keep going. Yeah. So like you can, if you exceed like 15 bits, you can just keep adding bits to the end and then like kind of like.
Right. But I would imagine that there should be some small gadget at the end of the protocol that maybe Alice is allowed to say, oh, you're already correct or something like that. Or
no, we don't have that. It would just be Bob. Yeah, it would just be like updating the length like X until the end of the protocol, and whatever you have at the very end, we just take like the first 15 bits and look at it.
Right, but then if Bob says, okay, here's a 15-bit message and it's already correct, what does Alice say?
Oh, she just like says maybe like 0, like add a 0 to the end, just like
an arbitrary stuff. Okay.
Yeah. It's a good question though. Yeah, actually, that's a good point. I'm going to skip over a lot of that sort of like edge cases in this talk, but it's something you do have to consider when you like make the protocol. Yeah.
So you mean this in an aggregate sense, right? You could still have a bad update, a bad update, but then you need 3 good updates to undo them, right? Like your backspace character could get corrupted, and then the Bob
yes
keeps appending.
Yeah, so like basically like there's sort of a potential function going on, like every bad update will be like, this is like one more negative progress, and then you have to like undo the negative progress, but yeah, it chains together. So. Cool. So yeah, so I guess the assumption we made here was that Bob is not corrupted. I mean, unfortunately, we have a two-way protocol. Bob is allowed to be corrupted. So I guess what do we do for that? Well, we won't be able to fully fix this until like later in this talk. But I guess one modification I want to make just first is that Alice is going to parrot Bob's question before she answers. So if she receives a question from Bob, it might be corrupted. She's going to then respond with like both like the question she heard, which you can denote X question mark, and also like sigma, which is 0, 1, or backspace. And so like, and this sort of like helps protect a bit because now Bob is only going to update according to sigma when X question mark, the question Alice is answering, is actually equal to his guess, right? Otherwise, it doesn't make any sense to update. Okay, let's see. Oh yeah, and I guess like one other thing is, so like before in the previous slide, I said there were 3 options for Alice's message at every point, right? 0, 1, or backspace. Now we have like, I mean, a variety of options. So I just want to say though that like the relevant this is okay though, because like when Bob receives a message, he's going to check like distance to ECC of X star 0, ECC of X star 1, ECC of X star backspace. So there's only 3 messages that are really relevant for like needing the distance 2/3. Everything else, like I guess, like hopefully you don't have to care about as much. Okay. Okay. So I guess like so from that, second idea is like, what if instead of so I guess like so in the previous slide we had Bob trying to learn Alice, right? But we actually need both parties to be learning each other. So let's just have them both ask and answer simultaneously, right? And hopefully this will give you 2/3 on both sides and then we'll be done. So that's what we're gonna do here. So now Alice and Bob both have inputs X, Y. Alice is gonna additionally have a guess for Y, which we denote Y star. And Bob is going to have a guess for X, which we denote X star. And so every message is gonna consist of 2 parts, a question and an answer. So over here we have like X star, the question, it's going to be the first half of the message, and the second half is going to be the answer. Okay, and this is the protocol, I guess, just so you know, like I'm not going to change it on you. This is exactly the communication, what everything is going to look like. The one thing though is like what code, like error correcting code do you use? If you use just like a normal error correcting code with distance 1/2, well, then the answers only have distance 1/2, right? And then you only have 1/4 like resilience per side, which is not good. I'll give you 1/8. So I have to tell you, I guess, like what code we're going to use. So the next idea is like we want to use an error correcting code with good distance properties. Yeah.
So I have a question regarding like the messages. So is the assumption that like the message that Bob wants to communicate, let's say Y is independent of X, like are these independent messages that we want to communicate?
Yeah. Any other questions? Yeah.
So just like how do you maintain efficiency? So like you want constant rate, so you are going to like most of the answers are already correct, so you already sort of need to know the last few constant bits. Is that like so if I'm communicating k bits, if I actually end up repeating k bits at every iteration, this is not a constant rate.
Oh yes, yes, exactly. Yes. So the protocol I'm showing here is not going to have constant rate. It's going to be like a quadratic in the input size, which is not good at all. There will be a separate modification needed to make it positive rate using like something similar to a tree code. So a tree codes like basically allow you to get the positive rate in interactive settings. And it's been used in a lot of previous like interactive coding works. But yeah, I guess I'm not going to do that in this talk. So this is more on like the resilience side and less on like the rate side. Okay, so we need an error correcting code with good distance properties. Like the 1/2 distance is not going to be good enough for us. Okay, so what do we want? Well, we want all the different answers like X star 0, X star 1, X star rewind. They should all be 2/3 distance apart. So graphically, it looks like this. So if you imagine all the code words are like in some Euclidean space, there should be like a cluster of like code words associated with the answer X star 1, X star 0, X star rewind.
So the question, why'd you leave the question out?
Oh, because, but yeah, because I guess like, let's see. I guess like you want, so I guess before we had like a question being asked, and then like an answer is, we want those to be 2/3 distance apart. And then I guess we add in the question, but the hope is like both sides, the answers will be 2/3 distance apart. It actually turns out like we can't really get 2/3 distance for both question and answer. It's just not a thing you can do. So that will, I guess, yeah, so I guess like we're basically asking for the questions to be 2/3 distance apart, and then we'll see what we can get for the questions. Does that make sense, or is that not a good answer?
You're saying that you want the answers to be 2/3 apart.
Yeah, we'll figure out something for the question first.
It's less bad if the questions get corrupted because the protocol will try to fix it, right? Because if it mismatches, then the protocol itself is gonna say, okay, so I don't update.
That's actually a good point, yeah, also, that,
I don't know the technicalities, but at least intuition seems to be that.
yeah, that's actually why.
This one is way worse that something
I see that
corrupts
this
it.
is the hard part.
Yeah, that's a good point, though, because like Bob won't update unless like the answer to the question is right also, right? So it's like if the question gets corrupted, you just don't update at all, and it's like kind of fine. Yeah, that's a good point. Yeah, so graphically we have this picture. So we have like all the answers corresponding to x star 1 here, answers x star 0 there, x star rewind over there. And the hope is like you can get this picture with 2/3 distance between any points in different clusters. Unfortunately, this actually won't be good. Like this is not a good ECC. And the issue is if you enforce this property, you get a code where inside each cluster, like the points are too close together. And it becomes too easy to corrupt to different question, so that like you would never make progress because you're always answering the wrong question. So this isn't gonna work.
So what's the best distance that you can get in each cluster?
Cluster 1/6.
1/6.
Yeah, and if you corrupt 1/6 of one side every time, that's like 1/12, which is even worse than 1/8. Okay, so what is an ECC we're actually going to use? We're going to use an ECC with these distance properties. So between any 3 different answers to the same, so fixing like the question and the answered question, then you can get relative distance 2/3 between the 3 different answers. Between every other pair of code words, there's going to be relative distance 1/2. Okay, so this is like a picture, I guess. So like, yeah, fixing like y star and x star, the 3 answers are 2/3 distance apart. And it's true for like every y star, x star. But like for instance, between these 2 points, that's relative distance 1/2. Okay, so it's like this seems like kind of good, right? Because you have relative distance 2/3 between like sort of like some pairs of answers, but like it's not clear that we've made any progress, right? Because like it's still relative distance 1/2 between some good answers and some bad answers. So like, you know, presumably the adversary could still just corrupt the 1/2 distance to like a bad answer, right? Half the time, and then you've made no progress at all. Yeah, so yeah, I guess this will end up being okay. And the key point is that when you corrupt to like a bad answer from like, maybe this is what Alice is actually trying to send, you have to also corrupt the question involved. So we'll be able to update with different probabilities based on the question being asked, in addition to like the answers. And I'll show you how this works in the next slide. Okay, is there any other questions for the slide first?
So you're saying that then you could detect it somehow and wait?
You actually can't really detect it, but like I guess the hope is like let's say that like Alice has already learned what Bob's input is, so she knows why, like y star equals y. Then if the adversary wants to corrupt her answer to a bad answer, they have to change the question being asked also. So Bob knows when like the question being asked is not like his actual like, you know, input, like the message in his head, and he's like, oh, that question, maybe that was corrupted or something, so maybe I should update like with less confidence.
That's what I meant. So you can detect the.
Yeah, I guess sort of you can detect it, yeah, in a sense. Yeah. Okay, so I guess so let's see what happens in an example. So I guess I won't tell you like all the details that go into the final construction, but this will hopefully give you like an idea for like this like how the step sort of works. So we're going to have so Alice and Bob again have the guesses y star and x star, and we're going to assume that Alice has already made a lot of progress, so her guess is equal to Bob's input y. Okay, and so let's suppose that Bob is at the empty string, so he has no idea what Alice's input is supposed to be. And he's going to send it over to Alice and be like, hey, I have this like empty string, like what should I do? And Alice is going to respond by telling him the next bit, like the first bit, I guess, of X, let's say is 0. And he's going to update and say, okay, so yeah, now my string, my guess is 0. Now he asks a question like, my guess is 0, what should I do? And let's say Alice is like, okay, the second bit is 1. You should update it as a 1. But now the adversary can come in and corrupt it using only like 1/2 of the message and get to a separate code word ECC of y prime, which is different than y, and then like the number 1 symbol instead, right? And now if Bob just like updates as before, he's going to delete the last bit, getting back to like the original state, right? He's back at its empty string. And so no progress has been made, and it only requires 1 corruption. So that was the issue, I guess, from the previous slide. Okay, so what's the fix? The fix is we're going to update with different probabilities based on the question being asked. So we're going to say that if the question being asked is equal to like the input that you have in your head, you're going to update with probability 1. So again, you still have X star equal to the 0 string. However, if Y star is not equal to Y, we're only going to update with probability 1/2. Okay, and so with 1/2 probability, we're going to end up back at the empty string, which is no progress made. But 1/2 the time, we will stay at 0, right? So 1/2 the time, we did make progress. So on average, like at least, like progress is still made. Right, okay. Does make sense? Okay. Yeah, I guess it's
Why don't we not update at all? Like why, like if Y star is not equal to Y, why do you want it?
Oh, because then you can't even start the protocol because both parties are like, we don't know what your input is, and then they can't update at all.
Oh yeah, in the beginning I understand, but once like you realize that Alice knows that your Y star, as in like Alice Y star is equal to Y, then after that you should expect the same to continue.
Should expect the same to continue. Oh, well, the one issue though is also like the adversary could like have them like make lots of progress, learn why, and then like cause lots of negative progress, and now they don't know why anymore, and maybe they swing to a different like value of y. Sorry, I don't know if that answered your question. Okay. Okay, it's okay. This is like the last technical point, so I guess yeah, we're done after this.
I have a random question, which is, so in here, I'd imagine that you really care about when the inputs are large, right?
Mm-hmm.
And when you're doing the protocol at a certain point, potentially your strings that you're sending as questions are very small, right?
Mm-hmm.
So do you actually pad so that they're large?
Yeah.
Okay.
You can pad.
Okay. Yeah. That was just my experience.
Yeah.
Because otherwise the rate won't work out.
Mm-hmm.
Yeah. Okay.
Yeah, so I guess like there are like a few other modifications you need to make to the protocol along these lines to make everything sort of work out. But this is, I guess, like one of the main ideas. So I just wanted to show you an example of how it worked. Okay, so and I guess that's really it. So like, yeah, so I guess in our works, we were able to determine the optimal error and erasure resilience of interactive coding schemes. And we have positive rate and computational efficiency. I guess I didn't really say why either of those hold, but like I guess positive rate, you can do some modification with like a tree code like structure. And computational efficiency, you use like a technique from like Ghaffari and Hoppler in like 2014, where they are able to like break down the protocol into small chunks and simulate them efficiently and then pad them together in a way.
That's only needed because of the tree code. The efficiency is because.
The tree code, yeah. The issue with efficiency, the tree code is like exponentially hard to decode.
Can you say something about the general protocol where they're not just sending?
Yes. Okay. Yes. That's a good question. So this protocol by itself, you can't actually apply tree codes directly to it, or we couldn't figure out how at least. So we actually needed to make a different protocol where you either ask or answer at every point. So you're never doing both anymore. So you're either asking or you're answering. So the kind of progress is made like sort of half as slow. But this is okay because when you use tree codes, you kind of build the question using a tree code at every point. I don't know, sorry, maybe this is too much.
Yeah, I'm confused because I thought the whole key was to do them at the same time.
Yeah, so I guess you
That's
ask for answer, but like you ask for answer adaptive. So if you see the previous person has just like asked a question, you would answer it. But if they answered the question, you would then ask it.
So from what I remember, for tree codes, you need the bigger alphabet. So binary is not enough. Right?
Yeah, you can. Yeah. So then what we do is you take a large alphabet tree code, and then you take the large alphabet symbols, and you just replace each large symbol with like a binary code.
So I have a question sort of in line with what Tony was asking. So, yeah, so in the chess game or something, again, it's like you don't have this simultaneous sort of asking answering, right? Like only after you completely understand what the other person's input is, you make your decision or something. So yeah, I think I'm just a little confused with the previous update operation. It seems to really rely on the fact that this answering asking
Yes.
happening at the
Yeah.
same time.
Yeah, exactly. That's actually a good. Okay. Yeah. So I guess like for like interactive protocols, how would you simulate it? Yeah, so this protocol we described just now heavily relies on like you knowing what the other person's correct output is supposed to be. But we don't have that anymore when you have interactive protocols. So instead, you're going to keep like a guess for the transcript in your head, and you're going to try to simulate it continually at every point.
So it's the same idea of getting back to the program.
Yeah. Yeah, and then I guess like you need to deal with like I guess update probabilities correctly. It'll become important to like once both transcripts match, then it's like very possible or like hopefully likely that the two will both be correct. In which case, then you update with different probabilities. Okay. And I guess like the last thing is just like the open question that Tony brought up earlier, just like, can we remove randomness from the protocol? Like why do we need to use randomness even before getting to computational efficiency? But actually even like getting computational efficiency without randomness is also a really important problem. Like it's just like remove randomness in general.
Wait, say that again? Getting computational efficiency?
Without randomness. Like right now, the ways we know to like get computational efficiency involve randomness because you would have to send like a hash of like something which needs to be randomized so that it like avoids collisions with high probability.
And right now, the only randomness is in the update probabilities.
Yes. Before you get to computational efficiency, it's the only place. Okay. That's all I had. So.
Somehow the sense that you shouldn't be able to remove randomness because it seems like you have to do some kind of equality.
Yeah.
But
For computational efficiency. Yeah, I don't know either. Like, yeah. I don't know.
I could be totally wrong, but I just can't picture how.
Yeah.
Any other questions?
Would this generalize to 3 players?
Oh, I don't know. I didn't look at multiplayer at all. Maybe you should look at multiplayer.
Okay, great. Thanks very much. So